definitely depends on the values given to the masses. We must select these values so that the motion of the center of gravity is uniform and rectilinear. This will always be possible if Newton's third law holds good, and it will be in general possible only in one way. But no system exists which is abstracted from all external action. Every part of the universe is subject, more or less, to the action of the other parts. The law of motion of the center of gravity is only rigorously true when applied to the whole universe. But then, to obtain the values of the masses, we must find the motion of the center of gravity of the universe. The absurdity of this conclusion is obvious. The motion of the center of gravity of the universe will be forever to us unknown. Nothing therefore is left, and our efforts are fruitless. There is no escape from the following definition, which is only a confession of failure. Masses are coefficients, which it is found convenient to introduce into calculations. We could reconstruct our mechanics by giving to our masses different values. The new mechanics would be in contradiction neither with experiment nor with the general principles of dynamics, the principle of inertia, proportionality of masses and accelerations, equality of action and reaction, uniform motion of the center of gravity in a straight line, and areas. But the equations of this mechanics would not be so simple. Let us clearly understand this. It would be only the first terms which would be simple, i.e., those we already know through experiment. Perhaps the small masses could be slightly altered without the complete equations gaining or losing in simplicity. Hertz has inquired if the principles of mechanics are rigorously true. In the opinion of many physicists, it seems inconceivable that experiment will ever alter the impregnable principles of mechanics, and yet what is due to experiment may always be rectified by experiment. From what we have just seen, these fears would appear to be groundless. The principles of dynamics appeared to us first as experimental truths, but we have been compelled to use them as definitions. It is by definition that force is equal to the product of the mass and the acceleration. This is a principle which is henceforth beyond the reach of any future experiment. Thus it is by definition that action and reaction are equal and opposite. But then it will be said, these unverifiable principles are absolutely devoid of any significance. They cannot be disproved by experiment, but we can learn from them nothing of any use to us. What then is the use of studying dynamics? This somewhat rapid condemnation would be rather unfair. There is not in nature any system perfectly isolated, perfectly abstracted from all external action, but there are systems which are nearly isolated. If we observe such a system, we can study not only the relative motion of its different parts with respect to each other, but the motion of its center of gravity with respect to the other parts of the universe. We then find that the motion of its center of gravity is nearly uniform and rectilinear in the conformity with Newton's third law. This is an experimental fact, which cannot be invalidated by a more accurate experiment. What, in fact, would a more accurate experiment teach us? It would teach us that the law is only approximately true, and we know that already. Thus is explained how experiment may serve as a basis for the principles of mechanics, and yet will never invalidate them. Anthropomorphic mechanics. It will be said that Kirchhoff has only followed the general tendency of mathematicians toward nominalism. From this his skill as a physicist has not saved him. He wanted a definition of force, and he took the first that came handy, but we do not require a definition of force. The idea of force is primitive, irreducible, indefinable. We all know what it is. Of it we have direct intuition. This direct intuition arises from the idea of effort which is familiar to us from childhood. But in the first place, even if this direct intuition made known to us the real nature of force in itself, it would prove to be an insufficient basis for mechanics. It would, moreover, be quite useless. The important thing is not to know what force is, but how to measure it. Everything which does not teach us how to measure it is as useless to the mechanician as, for instance, the subjective idea of heat and cold to the student of heat. This subjective idea cannot be translated into numbers, and is therefore useless. A scientist whose skin is an absolutely bad conductor of heat, and who therefore has never felt the sensation of heat or cold, would read a thermometer in just the same way as anyone else, and would have enough material to construct the whole theory of heat. Now this immediate notion of effort is of no use to us in the measurement of force. It is clear, for example, that I shall experience more fatigue in lifting a weight of 200 pounds than a man who is accustomed to lifting heavy burdens. But there is more than this. This notion of effort does not teach us the nature of force. It is definitively reduced to a recollection of muscular sensations, and no one will maintain that the sun experiences a muscular sensation when it attracts the earth. All that we can expect to find from it is a symbol, less precise and less convenient than the arrows to denote direction used by geometers, and quite as remote from reality. Anthropomorphism plays a considerable historic role in the genesis of mechanics. Perhaps it may yet furnish us with a symbol which some minds may find convenient, but it can be the foundation of nothing of a really scientific or philosophical character. The thread school. Monsieur Andrade, in his Leçons de mécanique physique, has modernized anthropomorphic mechanics. To the school of mechanics with which Kirchhoff is identified, he opposes a school which is quaintly called the thread school. This school tries to reduce everything to the consideration of certain material systems of negligible mass, regarded in a state of tension and capable of transmitting considerable effort to distant bodies, systems of which the ideal type is the fine string, wire, or thread. A thread which transmits any force is slightly lengthened in the direction of that force. The direction of the thread tells us the direction of the force, and the magnitude of the force is measured by the lengthening of the thread. We may imagine such an experiment as the following. A body A is attached to a thread. At the other extremity of the thread acts a force which is made to vary until the length of the thread is increased by alpha, and the acceleration of body A is recorded. A is then detached, and a body B is attached to the same thread, and the same or another force is made to act until the increment of length is again alpha, and the acceleration of B is noted. The experiment is then renewed with both A and B until the increment of length is beta. The 4 accelerations observed should be proportional. Here we have an experimental verification of the law of acceleration enunciated above. Again, we may consider a body under the action of several threads in equal tension, and by experiment we determine the direction of those threads when the body is in equilibrium. This is an experimental verification of the law of composition of forces. But as a matter of fact, what have we done? We have defined the force acting on a string by the deformation of the thread, which is reasonable enough. We have then assumed that if a body is attached to this thread, the effort which is transmitted to it by the thread is equal to the action exercised by the body on the thread. In fact, we have used the principle of action and reaction by considering it, not as an experimental truth, but as the very definition of force. This definition is quite as conventional as that of Kirchhoff, but it is much less general. All the forces are not transmitted by the thread, and to compare them they would all have to be transmitted by identical threads. If we even admitted that the earth is attached to the sun by an invisible thread, at any rate it will be agreed that we have no means of measuring the increment of the thread. 9 times out of 10, in consequence, our definition will be in default. No sense of any kind can be attached to it, and we must fall back on that of Kirchhoff. Why then go on in this roundabout way? You admit a certain definition of force which has a meaning only in certain particular cases. In those cases you verify by experiment that it leads to the law of acceleration. On the strength of these experiments, you then take the law of acceleration as a definition of force in all the other cases. Would it not be simpler to consider the law of acceleration as a definition in all cases, and to regard the experiments in question not as verifications of that law, but as verifications of the principle of action and reaction, or as providing the deformations of an elastic body depend only on the forces acting on that body? Without taking into account the fact that the conditions in which your definition could be accepted can only be very imperfectly fulfilled, that a thread is never without mass, that it is never isolated from all other forces than the reaction of bodies attached to its extremities. The ideas expounded by Monsieur Andrade are none the less very interesting. If they do not satisfy our logical requirements, they give us a better view of the historical genesis of the fundamental ideas of mechanics. The reflections they suggest show us how the human mind passed from a naive anthropomorphism to the present conception of science. We see that we end with an experiment which is very particular, and as a matter of fact very crude, and we start with a perfectly general law, perfectly precise, the truth of which we regard as absolute. We have, so to speak, freely conferred this certainty on it by looking upon it as a convention. are the laws of acceleration and of the